Okay, so we're in the middle of chapter 13, which is on policy gradient methods. And last time we sort of introduced the concept and introduced this short corridor example, which has this state in the middle where the actions are switched, which, if this was a problem where we could actually see each of the states, then the problem would be trivial because we could, end every episode in three steps. We would just go right and then, left and then right. We just have to alternate the actions because at the middle state, the left action is the one that takes us to the right. And, you can solve this exactly. I mean, what I just said is the solution you would use if you could do whatever you wanted in every state. But if we consider this as a problem where the actual state is hidden from us because we're using a type of approximation that maps all three of these states into the same feature vector. Now, that is very different from just creating a problem where there's like a 1/3 chance of the actions being switched, which would actually be like a legitimate MDP. But, you know, in this case, it's not that there's a 1/3 chance of the actions being switched, it's that there's a state we can't see and we don't necessarily end up in it, a third of the time. It's just 1/3 of the total states are like that. And actually, depending on the policy, the time we spend in this state will vary. So the problem is somewhat more complicated than that. But in this exercise, what you can do if you want to solve it is you can only consider policies that are stochastic policies that do the same thing or that have the same stochastic distribution in every state. So we define some probability P of taking the left action, just to simplify things. The right action is always one minus P in that case. And then you can write down, the Bellman equations for the states, which tell you the relationship between the state values. And after you go through a bunch of algebra, you come up with these expressions for the state values in terms of P, where P is this probability. And then you can, sorry. So these curves in this graph, it's sort of in this curve, what they're showing is the value from the first state if you vary P, right? And you can see there's this point which is optimal, which you can sort of eyeball on the curve. I'm also showing these other curves for the value at state 2 and 3. This would be like if you initialized an episode on a different state other than this. I mean, the most trivial case is if you start on state 3, because if you start on state 3, you can see this curve is just, it's approaching 1, or sorry, this value will approach the highest possible value as the probability of going right approaches 1, because we can completely bypass this switch state. But the more difficult case is from state 1, and we have the lower curve here. And if you solve this, these end up just being equations that you can optimize, and you wind up with a quadratic equation when you try to set the derivative to 0. And you can find that the optimal action, sorry, for state 1 is, P left is this, 0.414, but it's just root 2 minus 1. And P right is, is 1 minus that. So, about like 59% to go to the right. And, like this actual, like there's no way we could define, like turn this into some kind of tabular problem, because what actually happens or when we select actions, like the reality is it depends on the order of actions. Like if you were to observe this problem, you would notice that if you started out, like every single time that you went, right, left, right, right, you would reach the goal, but that requires you actually remember like the history of actions, which in all these problems, nothing about the problem is allowed to depend upon like the history of actions. All the information has to be contained within whatever current state you're in. And of course, if we know the actual state we're in, we don't need the history of actions. We could recover that state information if, in addition to looking, if we're mapping all the states to the same feature vector, we could like recover the information if we could look at the history of actions, but that's not like a part of any of these solution methods. Like we're not actually, that would be a totally different kind of problem. But the point is like this setup, like this construction where there's this hidden information is just an artifact of the approximation method that we're using, not of the problem itself. Because like the problem itself, if we actually hid this information, it would no longer obey this Markov property where all the information that we need is contained within the state, because we clearly have this hidden information affects the solution a lot, and is not just simply a matter of the probabilities, right? Because like the actual probabilities we observe of reaching the goal are going to then be affected by the policy we use, because when these actions get switched depends on the probability of being in each state. Like how often we observe this switching of the action also depends on the policy. So they are intertwined. And during this proof of the policy gradient theorem we did, which is in this box here, you end up with like some of these expressions are converted to statements about probability. Like here, this means like the probability of transitioning from state S to a new state X in k steps under the policy. But exactly how these probabilities work and how they get, like what you get when you sum them all up, because like if you sum a distribution, um, over the like whatever the distribution is a function of, then you always get one, right? But if you sum it over some other quantity, you don't get one. And like in this part of the proof, we take this sum of this distribution over, something that appears inside of it, which is this k value. But we don't get one. We get this quantity, which is the expected number of visits to state S. And I thought maybe it's a little easier to see what's going on if we use this corridor example, this example here with different policies, we can try to visualize what these distributions look like. But in order to do that, there's this function I'm going to define. And all this is going to do is collect data for this grid world policy. So what it's going to do, I'm going to run it for a certain number of episodes, and I'm going to use a policy like we've defined here, which is there's some p. In this case, it's like this is p left, and p left is the same in every state. Okay, so we're forced, like here it is here, if and the actions here are indexed, like 1 is going left, 2 is going right. So here there's just some probability p of taking the first action, and it's always the case. And I'm going to run through all these episodes, and I have this matrix called state visits. Actually, sorry. Okay, so no, state visits is, yeah, it is a matrix, and what it does is it keeps track of, for every step in the episode, which state am I in. So for a single episode, obviously this is just going to be, ones, but I'm going to run this for a lot of episodes, add this up, and I'm going to accumulate like all of the statistics of when a state was visited. So here, there's only 3 states in this problem. And you can see like the result of collecting this data once. And you can see that because all the episodes start in state 1, the first row of this matrix, there's just 1 million, counts in state one. And then as you go forward, these counts start getting distributed between the different states. And by default, this is just going to use p equals 0.5 when this runs. Okay, so yeah. So does that make sense to everyone? Like what's being collected here? That I'm just sort of collecting statistics of how many times a particular state was visited on every time step that I observe. And like at the bottom, these are zeros, or there's just like a one here because there was only one episode I ran that got to this, 134 steps. Whereas, early on, every single episode will visit, will be in the first state on step one. So now you have these are just, individual numbers I've collected. But then depending on how you normalize this, you get different probability distributions. So, I'm going to, when I refer to this matrix, I'm going to refer to it like this, where n, this is like the number of visits, and then sk is just for the state, and k would be the step it is visited, or the row of the matrix. And whatever distribution we make, it has the condition that like whatever the distribution is a variable of, if we sum over that variable, we should get 1. And we always have the case that on step 0, we always like initialize this in state 1, and we're following this policy with a probability p. So we have this full visit count. So also, note that if we want to know just like the total number of visits to state S, we would just sum, for a particular S, we would just sum, all of the Ks, right? And that would give us this. And like similarly, if we want to know the number of times we reach a certain step K, we would just pick a particular K and we would sum, over all the S's. So here, like for example, there's only one time, or like one episode. I mean, this is really like the number of episodes we reach step K, but see, there's only one episode in which we reach this 134 steps. And here, this is also 1. And now, this is 2, right? So there were 2 episodes that reached this number of steps. And then, of course, initially, every single episode we ran will have this visit count. So then, we could write down this full probability distribution, which would tell you the probability of reaching a particular state on a particular step. And this distribution is one in which you have to sum over both the states and the steps to hit 1. So like the probability is like the actual probability values are distributed across all of those possibilities of both the visit count. But we can form simpler distributions. Like if we want to know what is the probability of reaching a certain step K, or not, of observing a certain step K out of all of the different, steps, counts that we could see, then we would just take the full distribution, right? And we would sum it over all of the states at a particular K. And that's like summing across a row of this, once this has been normalized, right? So you can imagine, like, if I take this matrix and I divide it by the sum of everything, then, this would be converted into, a bivariate probability distribution, this one here. And then similarly, I could sum for each row along the whole column, and that would tell you the probability of being in a state. And this is the distribution that we've often seen used in the book, which is, like the stationary distribution over the states. I mean, often it's used in a continuing problem, because for an episodic problem, this does depend on the starting state that we're in. It's only for a continuing problem where you get this, which is independent of where you start. But in this case, because I'm using the visit count, it doesn't matter. This is just like for a particular episode starting on, on this state. If I sum the column, right, and divide by the total number, then I get the probability of being in a state, regardless of what step we're on. And then you can also get a more granular distribution, which is, you can ask, okay, if I fix a state S, then what is the probability of seeing that state on every given time step? So like for state 1, for example, if I look at like in a given episode, the probability of being in state 1 for each step k, such that if I sum over all the k, this would be 1. So it's telling you, like, when you do visit a particular state, how often does that visit occur on which step of the episode? And you can also have the same thing where you can pick a particular k value, and you can ask, what is the distribution over states, like this thing, but at a particular k? So this distribution over states is for all k, like it's summing up over all k. Whereas this one is saying, well, no, let's say I'm on state 1. What is the state distribution? Obviously, for this problem, on state 1 or state 0, however you index it, you have 100% probability of being in state 1. And then we can see on step 2 of the problem, right now, the probability is distributed, depending on what p is, between these two states, right? But there's still a 0 probability of being in state 3. And then as you evolve this out in time, as you go to higher and higher steps, this distribution changes. So you can, compute all these distributions once you've collected this matrix. And that's what I've done here. So it's sort of showing this in the same order that I had originally. But here I've actually, we can make this a little more extreme. Like I'll make, this is actually now set to like the optimal policy, or close to the optimal policy, where p left is like 0.4, or close to 0.4. And you can see here, this is the probability, this one, of a particular step k. So if you actually calculate, like this can be used to calculate also the expected number of steps in an episode. On this plot, this blue line is showing the density function. So that's like the probability of each step k. And here it's a little hard to see, but this probability decays as you go out. And of course, it's at this constant value for the first few steps, because every single episode, has to go through at least 2 steps before reaching the end. And the probabilities start dropping as you go out here to increasingly higher numbers of steps. But I also have the distribution function here, as well as the density function. And here you can see like the median value. So for here, the median value is, between 5 and 6 steps for an episode. And you can see where you get to like, 99% of the episodes are 50 steps or less for this p. Now, if I move this from the optimal policy, like if I make, it's 0.9 or something, I can recompute this, and you'll see that now the median value is much higher because the policy is worse. It takes longer to complete episodes. So here the median value is now, around like 25 steps. And if we go out to 50, only 75% of episodes are less than 50. If we look more closely at this, we would still see the same plateau at the start, again, for the first two steps, and then the decay rate is just slower because there's a much higher chance of now having longer episodes. And this plot here is showing the full distribution. So at every point here, it's saying, like, what is the probability of on step 10 being in state 1? And this is like two-dimensional because, we have these two different variables in this bivariate distribution. And then this is the stationary state distribution, or not really for the episodic problem, but this is just the distribution over states. So this will also change. So this is for p is 0.9. So there's a 50% chance. So this is p left. So obviously, if I make p left higher, we end up spending more time in state 1 because there's more times when we actually go left from state 1. And then if I change this, let's say to 0.1, this is actually much closer to the optimal policy. We'll see now, well, actually, okay, this has dropped slightly. It's still pretty close to 0.5. But really what's happened is the probability of being in state 2 has risen a lot compared to 3. But for the rest of this, I'll just set this close to the optimal policy again. And then we can see under that policy, it's a more even distribution across the state space. And then this is showing, if I take each one of these now, this is showing this distribution, right, where I fix S and I look at how the visits to that state are distributed across steps. So there's 3 of these because there's one for each state. Here, you can see how there's this sort of alternating pattern at the beginning of the first few steps, but it ends up, evening out. That those oscillations die out as you get out here because everything starts getting randomized. And if you put them all together, you can see how they compare. But I mean, this one is it's harder to interpret, and also like the probabilities drop off a lot as you go to higher steps because we're also just unlikely to see episodes of this long anyway. Like the median length is between 5 and 6 steps. So most of the probability is concentrated in this first part of it. What we can see is as we get out here, right, like in order to complete an episode, we have to be in state 3 and we have to go right. So, the relative probability of being in state 3 compared to the others, you can see as we go out here, is rising, right? For this distribution, over all the steps, we have a higher, being in state 3 is the lowest probability, right? But if I compare the probability as we go out to higher steps under this policy, and there's some point where you can see around 5 or 6 steps, we have this large, or at least, no, actually this is for 3 steps, but you can see like the reason why this policy is eventually working is because we're boosting the chance of being in state 3 enough that eventually we will have a case where we're in state 3 and we take the right action. And then finally, all of these distributions, this is the last one I wrote here, which is for a fixed K, what is the probability of being in a state? And this one where if we sum over the states, we get 1, like that's what's being shown here, where this is now not for a fixed K, but summing over all K. And then these plots are for a fixed K. So I already said, like in step 1, you're only in state 1. In step 2, right, you're split here about 60% of the time you're in state 2, 40% of the time in state 1. And then as we keep going, we end up, getting this new distribution. And I'm showing here, the first 5 and then skipping 10 steps up to state 50. And then as we get out to these really high step counts, the reason why these look so different is because this is where we don't have very many samples, right? Like this final step here, we only have 1 sample. And of course, the 1 sample we have is going to be in state 3 because that's the state you have to be in before terminating an episode. But, some of these in the sort of the middle part where we expect, a lot of the episodes to live in, there's this long period of time where the distribution across states is looking similar to the full stationary distribution, with obviously the state one probability being a little bit lower. So what's actually used in this proof, this distribution, this is actually one of these. So what's being summed here is being summed across K. The reason why we don't end up with 1 when we sum this is because we're not summing over S. I mean, the sum over S is happening here. Each one of these distributions, if we sum over S, which is summing all these 3 values, we will get a 1. But what this sum is doing is it's taking a particular S, so like, let's say 1, and it's taking the value from each of these distinct distributions and summing that up. And that value ends up being this expected visit count, because it's not actually, like, this probability distribution is a function of S, not of K, but it is a separate distribution for each K. And to really see this, like how this value is the expected visit count, you have to go back to these definitions of, like, normalizing the counts and seeing exactly what you're summing. But it's sort of glossed over in the proof. But when you write stuff down like this, I mean, that's why I wrote these distributions out, being very clear as to what the random variable is in the distribution. So, like, if you sum over the random variable, you end up getting 1. But if you sum over other things, you get different values depending on how the distribution is structured. So yeah, I don't want to belabor it too much, but I just thought this, I don't know, this part of the proof can be a little confusing. And I think if you actually look at the counts, then you can get a better sense of how all these different distributions are defined and what they look like for a particular example. So, are there any questions about this or the policy gradient theorem proof? So the next thing I was gonna talk about was, I mean, so we had last time we derived reinforce this algorithm after we had the policy gradient theorem result, and we also had derived, like, in order to implement reinforce, we have to compute this eligibility vector here, which is the gradient of the natural log of the policy function. And we had this expression for the eligibility vector in terms of the softmax. So there's this added assumption that we compute some vector h, where here, like in the linear case, h is just going to be some vector which we get from taking this matrix multiplication of the parameter matrix with the feature vector. And then we convert h into a probability distribution with the softmax function. So what we really want, what this is showing, is if we go through that, the natural log of the softmax of h and take the gradient of that, we have this simpler expression where we just need to know the partial derivative of, like, the preference vector with respect to the parameters. And this, in the linear case, this simplifies right? Because this derivative is just going to be the value of the feature vector at that index, right? So we have like simplified versions of this. Now, in general, like with nonlinear approximation, you do have to have some way of computing these partial derivatives. But if we know we're dealing with the linear case, and even simpler, if we know we're dealing with binary features. So in the case of binary features, our feature vectors are either, it just has a series of values that are either 0 or 1, depending on if the feature is active. So for binary features, we really need this function f, which tells us which features are active. And then here, to compute this gradient, we just have these really three cases where a lot of the updates, a lot of the gradient values are just 0. And then we have this value of 1 minus whatever the policy probability is in the case where, if we're looking at the part of this parameter matrix where the column corresponds to the action, and then where it doesn't correspond to the action, I mean, so really we have this negative pi factor everywhere, and then we just add a 1 in the column that corresponds to the action. So there's sort of three cases to consider. I mean, there's always the generic case, and actually I'll just show the implementation of this with baseline. But here, well, we have the pseudocode in the book of reinforce. Ignore the baseline for now. It's just this v hat, which in the case without the baseline, this is just taken to be 0. So this is just a generalization of the previous reinforce algorithm, because we can always take a baseline that just produces 0 regardless of the state. But you can see like this function is just designed to have, I mean, it's going to update the parameters, and it needs like placeholders to update the eligibility vector and the state value gradient, and functions to do the update. Then what actually happens in the loop, it's a little more verbose than what happens here, because like there are steps here that aren't being written out explicitly. Like when we compute this gradient, these functions actually take the feature vector as input. Not like here it's written as a function of the state value, but in the case of approximation, you see these steps here where this actually happens. But when I go through the episode, see, I have to update the feature vector with whatever the state is. And then the value function operates on the feature vector with the parameters. And the gradient update also operates on the feature vector. But there's just a few extra steps here to handle the nuances of how you actually compute this, so that you do it efficiently and you're not allocating a lot of memory every time you want to get a gradient or a feature vector. So all these functions are written in terms of actually updating vectors and gradients rather than producing them new each time. But then if we go back to the reinforce implementation, because of this simplification of when you use binary features, it is more efficient. So the easiest thing to see here, this is the version of the gradient update with linear features. So here, the parameters are just some either vector or matrix. The gradient is a vector or matrix of the same size. And then there's some step size parameter here. So here, the way they've written the gradient update here is they're saying, we just compute the gradient and then we add it to the parameters. And this implicit here is the fact that this is being, broadcasted like in programming speak, where if these two things are the same shape, then we're just adding them in an element by element fashion. And that's what's being done here. If these are just simple arrays or vectors, I mean, this isn't in the Julia language. This is just how you would do this element by element broadcast. In other languages, it would be different, but we're just going through each entry in this, and these things are the same size, they match up. So we're just doing this update. I mean, here, yeah, we have the learning rate times delta, but this ends up just being a constant value. So that constant value is just being represented here. Now, in the case of, let's say we have like a neural net or something instead of linear function approximation. Well, I have some implementation of neural net where the parameters are just, instead of being a matrix, there is some, this, if you look at what this data type is, this is just like a placeholder, but this is just a container that contains a few different matrices and vectors, which contain parameters and bias vectors for different layers in the network. And because I want the other function, like this, the function that goes through the loop, to be somewhat generic, like I could just write this line like they have here in the function, but then you need to make sure that whatever this, I'm basically replacing this plus function with this more general update params that has the same number of arguments. But this way I can define what I mean by like broadcasting across everything. And in the case of the neural net, it means that I have to loop through like the actual layers and whether I'm doing the biases or the parameters. And then each one of those inside of there is just the same as what the linear parameters look like. So then I can just apply the linear version of the function once I index through that. Now, the one that looks a lot more complicated is the one where I have this special data type for the binary eligibility vector. And that's because in the binary case, like I've shown here, in the previous two cases, whatever the eligibility vector or the gradient is, it has the same number of elements as the parameters. But in the case of in the binary case, a lot of the updates are just 0. So this is a way to just have a more sparse version of this, where if I know ahead of time that I'm only using binary features, then I don't actually need to save all the gradient values. I only have to save the values that are non-zero, and I don't even really have to save the values that are non-zero. I just have to be aware of what the active features are. And then if I have access to whatever this pi is, then when I get time to do the eligibility update, all I have to do is go through the active features and apply this rule. And that's what's being done here. So I have this custom thing where what I do when I sort of generate the eligibility vector for the binary case is I just save whatever the pi values are. I don't even have to make a copy. I can just point to them. And then I need to also keep track of what the active features are. And then this function here, these are sort of also computing the gradient at the same time as they're going through the active features. Whereas in this case, for the nonlinear linear case, I've already run some function which is computing this gradient. And then all I have to do is add it up. Whereas when I do it for the binary vector, I don't explicitly compute the gradient. I just keep track of what I need to apply this rule, because it has this special form in the case of binary features. And the only point of doing this is just so, I mean, if you really have a problem where the feature, like we had the example of the mountain car problem or the carpole problem, where you can make with tile coding like really long feature vectors, like thousands, tens of thousands, but there may only be like 10 active features at a given time. And then you save a lot of computation by just skipping over the 0 values and just applying this in a sparse fashion. So that's why I have here, this is this like special struct that does the binary feature vector, where all I do is save the active features. And this is just done this way so that I just save as much space as possible, and I don't allocate, like whatever I've allocated for active features, I don't have to reallocate it later. Yeah, and in the case of, sorry, so I was going to get to the reinforce with baseline implementation. In that case, I do have to define, in the case of the linear value gradient, again, when I update it, right, like for linear approximation, the gradient is just equal to the feature vector. So that's trivial here. It's also true in the binary case, but in the binary case, I'm not actually going to save the gradient. I am just going to save the active features and keep track of the number of active features. Because then when I go to update the parameters in the binary case, it's only going to go through the active features. Whereas normally when you do this update, it's actually just going to be the same as the one up here when I do this parameter update in the linear case where I'm just adding. You'll see when I have this update params with gradient where instead of the eligibility vector down here, yeah, update params with gradient. Yeah, see where this is now a binary feature vector. So here it's just doing the same element by element addition. It's just that it's only doing it on the active features and it's only adding one, or in this case, it's adding the constant here, whatever, the learning rate times delta is. And it's just, effectively not doing the summation for all the zero values because it is not necessary. So that's why in this code you'll see there's all this sort of preliminary stuff established. To do that, I mean, in the case of nonlinear function approximation, there's a lot more stuff. I have to set up additional things like the activation matrices and things that are fed into like the neural network cost function. But at the end, the actual implementation, like all of the complexity of all those different forms of approximation is just going to be contained within this, whatever the update eligibility vector, yeah, update value gradient. And then I can just use this generic update params with gradient inside the loop. And if this happens to be a binary feature vector, it'll just do the appropriate thing, which is, more efficient than if I were to use the linear version of it. I mean, you should get the same result if you do it the linear way or the binary way. It's just that, yeah, in the linear case, you're wasting a lot of values because you have these sparse vectors where a lot of the values are zero. But then you can see here, like when I define this with binary features, or it's easier to see with linear features, but I just call this function and I'm just filling in the appropriate, like update linear action preferences, update linear eligibility vector. And all I have to define for this case is the function that updates the feature vector. I mean, this will always be necessary. In the binary case, this is replaced actually with a function that gets the active features rather than updates the feature vector because the active features are all that's needed, the number of features. And then if you go back, I sort of re-implemented the reinforce algorithm I showed last time. We can see what this looks like, right? Reinforce. So we have, in the case of reinforce without a baseline, we only have the policy function and the policy parameters. So here, if I'm calling reinforce with baseline, I've also set this up so the arguments that would be pertinent to the value function are just nothing. So here, like these two arguments would be the value parameters and the value function gradient, and they're both just nothing. And then I have these other functions that update the value function gradient, and those return either nothing or zero. This is the function that returns, the baseline value, which in the case if we're ignoring a baseline, it just returns zero every time. And that's why up here, you have this version of the update parameters with gradient where both arguments are nothing, and then it just does nothing because, it knows that you're not actually using the baseline. But to show how the baseline works in the first place, we had this equation which told us how we can compute the gradient of the performance metric with respect to the parameters. And this originally, right, we had this expression, right, where it's written out here, right, sum over mu. So here, right, this is without baseline. So now the statement is that consider some baseline function, which it can be a function of S. It doesn't have to be anything in particular. The only requirement is that it can't vary with A, where A is the action. And the reason for that is we can see that if we separate out this sum, right? So like we can separate this into two terms. So the first term is just the original one we had. And the second term is the sum over the actions of the baseline function times, this gradient of the policy function. Now, because this doesn't depend on the action, we can factor it out of the sum. And of course, because the gradient is a linear function, we can also take the gradient on the outside of the sum. But this sum is a sum over a probability distribution, right? Over A, and we're summing over A. So this is just a constant. It's always 1. And the gradient of 1 is 0. So this term we've added, the baseline term, it doesn't actually, in the expected value, it does not affect the gradient at all. Now, of course, when we actually implement this, we're not going to sum over A. We're going to do sampling. So it won't actually be exactly 0. It will just be 0 in expectation as we take samples. But what it does do is it greatly reduces the variance of the gradient from the baseline. So it doesn't change the expected value of the gradient, but it does reduce the variance, which is very helpful in speeding up the convergence of this. And, we end up basically deriving the same update equation, except that this target value that, right, we're sampling with G, the state action value, in the Monte Carlo case, right, we're just taking a sample of what the discounted return is. But now we're just going to take that value and subtract whatever the baseline function is evaluated at state S. And it doesn't have to depend on S, right? Like the baseline value could literally just be a constant value, right? The reason why this, like we can't do the same trick here and just say that this whole gradient is just 0 is because this Q function depends on the action, right? So we can't actually take this trick. As we do this sum, we can't factor out Q from the sum. Oh, sorry, Krishna, you had a question. Before understanding the book, this book, I believe this book has a section that explains all the symbols and what they mean. I think it's at the beginning of the book. Let me see. Yeah, here. See, summary of notation. So I'm not sure if you meant this, but there is this summary of notation in the book, which explains. Also, if you read the earlier chapters, it kind of goes through. There's like additional notation and stuff that has further explanation in some of the early chapters. In my notes, I mostly use the notation in the book. If I use something different, I try to also explain it in the notes themselves. Back to where we were. Okay, so empirically, we'll see that this baseline ends up helping with convergence a lot. But the justification for why we can add it is just that the baseline function doesn't depend on A at all. And one natural option to use for the baseline is just a value estimate, like when we did value function approximation, right? We already did Monte Carlo, right? Gradient approximation with Monte Carlo for the value function. So we can actually apply that to reinforce with baseline. And we can see here in the reinforce with baseline, now we have additional value function parameters. And for convenience, I'm just going to reuse the state representation between the policy function and the value function. So in the linear case, let's see the linear value function, we have just the feature vector. It's another reason why I'm only encoding the state as a state feature vector, as opposed to a combined state action feature vector. There's not really any particular way you're forced to do it. They're all valid ways of doing the approximation. But just in my case, the parameters of the policy function become a matrix instead of a vector. But the feature representation in the linear case is just a vector. For the state value function, the parameters are also a vector, and the value approximation is always just the dot product between the two, which is why the gradient is always the feature vector itself for this. But the state value approximation inside of this loop is exactly the same as what we had before when we did policy evaluation with approximation in the Monte Carlo case. And here we're still in the Monte Carlo case where we're running an episode. We have the list, the state history of what happened in the episode, which means we can always compute what the return value is. Here, I'm computing the baseline value using the value function with whatever the current state feature vector is. And then the delta term using the gradient update, the gradient update is exactly the same as before. It's just the delta term now has included in it this subtracted baseline value. And then at the end of the process, we're going to have all the same information, but on top of that, we're also going to have a value function as well as a policy function. So we can test it here right now. I already showed this example of testing reinforce. This is just showing the reward per episode. So as it learns to finish faster or has the more optimal policy, this gray line represents the ideal value if we use the optimal value for P. So we can see how quickly it's converging. And we can compare that to reinforce with baseline. But here I will just test it. This is just to confirm the functions are actually working. But this is just running the version of this with the corridor MDP. Everything is the same with how the feature vectors are set up. And if you run it with binary features, you have to, provide this get corridor features function. If you do linear features, you have to provide the function that updates the features. And then in the nonlinear case, you have to define this. This is defining like the number of neurons in each hidden layer. But all these functions are running. If they produce a value of, whatever, 0.6, close to that, it means it's working somewhat well. But we can see more specifically what's happening with convergence if we look at this plot. So here in the book, it's showing how with baseline, it converges faster. Of course, you can see there's these two parameter values we have to pick. Here they've just pre-selected one that works well. Here I'm showing some different examples. So this is showing the reinforce without baseline. And then all these other curves are the version with baseline using different values of the two different learning rates. We can see I got the best performance for this pink one, right, where the learning rate for the policy parameters is 2 to the -7, and for the value parameters is 2 to the -2. The one they have in the book is, but you can see they're all quite good. They're all converging fairly quickly. If you really want to see what's happening in more detail, you can do a parameter study, which is what I have done here. So the parameter study is just doing this, but it's looking at sort of the average reward per episode over this curve. So it's like taking the mean value of these curves. And these also start, you can see the way this parameter study is run. It has this intentionally bad parameter initialization, which is why these all start at like -80, -90. If you initialize the parameters in this way, the policy you're dealing with, if you look at the example, it's prioritizing the right action a lot, like over here, and you wind up with an expected episode length of about like 87 steps. So that's why it's initialized here to verify that the algorithm is actually moving towards here. If you started with 0.5, like the problem is it should learn the optimal, but P of 0.5 is already fairly close to the optimal value. So you won't see that much of an improvement. So here for these parameter studies, I've started them all with the bad initialization. And then you can see here's the reinforce without baseline. And then these curves are for reinforce with baseline. The x-axis is the policy learning rate. And then there's different curves for the baseline because, I have to try out different of the value function parameter here. And you can see that the results on average are much better for a wider range of parameters. The best result I got is for this green curve. So again, -2 to the -2. It's similar to this curve here. And at this, let's see, I'm running over, yeah, this value, it's about 0.006 is the policy parameter learning rate. But these parameter studies we had done before in the bandit problem and some other examples. But here you can see clearly how much better adding the baseline is. And then this is the result of running it. If I pick out like this best parameters and run it for even, well, no, here I'm doing it for 100 episodes. Yeah. This parameter study is only over the first 100 episodes. And you can see I can run this like doesn't take very long to run it. You can see as I run it, this is the actual action probabilities it's found for the state. So, ideally this should be like 0.6. You can see it's sort of, there's still quite a bit of variance because of how long I'm running this, but you can see it's in the right ballpark. And if I run this for, let's say, 1,000 episodes instead of 100, it should produce more consistent results. Yeah, but around 0.6, you can always, lower. If you run it for more episodes, it'd probably benefit from an even lower learning rate, but you could always do the parameter study again for more episodes. Yeah. So any questions about the implementation with baseline and why the results are better when you add a baseline? So the baseline usually is not constant. In this case, right, it can depend on, right, the derivation. It's assumed to be a function of S. In this case, it is a function of S because we are using the state value approximation. Right, so our state value function will depend on S, and that's what we're going to use for the baseline. But it could also be a constant value. In this problem, it doesn't matter because there's only one state representation. So effectively, the baseline is a constant for this corridor example. But in general, it will not be a constant. It will, yeah, it could be any function of S. but we might as well just use the, like if we're doing linear approximation, we might as well use a linear approximation function that depends on S, that we learn with, gradient Monte Carlo, which is what is being done, done in this pseudocode, right? This is the step that does the gradient update on the value function. So now we can move on to, first I should point out, so yeah, the reinforced method is great, Monte Carlo, but sometimes there was a reason why we introduced TD methods earlier in the book. And the reason was because sometimes they learn more efficiently and faster. They have the advantage of, we can compute the target value. Like in the case of Monte Carlo, right, this G value that we're using for our estimate of the state action value, this we only know when we finish an episode. So at least for the first episode, there's no changes. Now, if you have an environment where you can have policies where the episode never terminates, then that's a problem, because then we'll never actually finish an episode and we're going to run out of steps. So even ignoring the fact that sometimes TD learning can be more time efficient, there are cases where if we're unable to do updates in the middle of an episode, we actually we may never learn anything, because right, we'll get no information until the episode ends. So that is why these actor-critic methods are introduced. And in the case of the actor-critic methods, we are going to take, again, right, so the baseline value part is the same, right? We already introduced the baseline. We know the baseline doesn't, we can do it as long as it's only a function of S. Now, this modification is that we're now replacing G of T with just the one-step return. And the one-step return means we sample one reward and then we bootstrap with the same value function at the next state, right? And the expected value of this, if the value function is accurate, which initially it will not be, but we do expect, right, this will cause the value function, it should converge, to something. I mean, it turns out that we don't need to do, we can mix and match techniques. So for example, the state value function, right, this doesn't show how we update the state value function. Here in the one-step actor-critic method, they are assuming that we use delta, the temporal difference error, to update the state value function. So here we're doing semi-gradient learning for the state value function, right? And then we are doing the eligibility vector update, and we're using this delta, which is the same TD target, to do the update. Now, this V hat could be learned differently. Like, let's say we did have a complete episode. We could use the Monte Carlo return for V hat so that our value function estimate was actually, not was actually converging to the correct value. But right, because we're using function approximation, we don't actually have a guarantee that this bootstrap value is this combination is an unbiased estimate of the return, because depending on how we do the function approximation, and remember, this target value we're using, even if we do it with Monte Carlo learning, it is based on the value error method, because we introduced the value error, and depending on the approximation we're using and what exact state we're in, the actual difference between that and the true value is actually state dependent, and it's certainly not unbiased. It's not random either. It's a particular artifact of how we do the approximation. So again, we do introduce some bias into the gradient here, not in the baseline. The baseline is irrelevant because, again, no matter how bad our approximation is, the baseline is not going to depend on the action. And we already showed mathematically, if it doesn't depend on the action, we don't have to worry about it, biasing the gradients. This part may introduce some bias, but we hope, and this also requires that our value function approximation actually, be doing a decent job, right? Because we're actually depending on it now to estimate the discounted return. Whereas with the baseline method, the value function approximation doesn't have to be anything good. It doesn't have to be that sophisticated. It is just there to reduce the variance. Here, we're actually depending on it to compute, right, this target value, to compute the delta here. So it ends up mattering a lot more, which could introduce some problems. But we have the advantage that now we can compute this delta after every single step. We don't have to wait for an entire Monte Carlo return. So if we look here, sorry, and a lot of the code can actually be reused because when we actually compute the gradients and we compute v hat, right now we do now have to compute v hat at the next state, but we already had a function for computing v hat at the current state. So really, this whole thing, we're now going step by step. We're doing the update in the middle of every step. I have these conditions here where you actually check if an episode is terminal, then you have to reset some things and reset the state value, right? When we have to reinitialize it, because this is designed to run for either some number of episodes or to terminate after some number of steps if we have an incomplete episode. But really, this is also suitable to use for a continuing problem because we can set the max steps, and this will have some feedback, and we'll still do gradient updates, even if we don't complete a single episode. It's just that, like if we choose to save all the step information, we'll get that. If we only save episode information, we won't actually have anything if the episode doesn't terminate. But what's being done here is just, again, it's the same as in this pseudocode. Yeah, there's just some extra steps. Extra things are reset, and when I initialize the state, I update the feature vector for the new state. There's also this term, instead of like forcing your approximation function to guarantee it to be 0 at terminal states, it's actually easier to just here, whatever the MDP is, it should be able to tell you if the state is terminal. And if that's true, then don't even bother computing the value function, right? We just define it to be 0, and then we compute the delta with the temporal difference delta where we have, right, the reward plus the discounted next state value, and then we subtract the baseline value here. So, we also saw in the last chapter how we could use eligibility traces. So this is using, right, one-step Actor-Critic because all of the target values here are based on the one-step TD error, right, this delta. Now, what the eligibility traces do is, depending on the value of lambda, they combine a sum of different n-step TD errors with different exponentially decaying weight terms. But all the complexity of that is hidden away in just tracking the gradients through time. So here, notice that when we do like this part of the update will match exactly what we already did for policy evaluation with eligibility traces, right? Where we just accumulate the gradient in the eligibility trace, and we end up decaying past ones depending on what the value of lambda is here. So lambda just tells you like how quickly do we stop caring about future n-step returns or looking back, ones. This is sort of like a backward-looking view of it. But if lambda is closer to 1, then that makes this a Monte Carlo method where we are tracking all the gradients through time, and we end up, by the time we end an episode, we have accumulated, all of the gradients, which just means that we actually care about the update and whatever state we were in at every point in the episode. And then if lambda is 0, you can see that this whole algorithm reduces to the one-step actor-critic algorithm, right? Because if lambda is 0, both eligibility vectors are just exactly equal to either the gradient of the state value function or the eligibility vector for the policy, right? And then this update step here, when we add this z, all we're adding is this, which is equal to this. So this is just a superset of the one-step policy, so you don't really need both of them. But if you know ahead of time that you're using lambda equals 0, you might as well use this because it eliminates, these extra steps that are actually irrelevant here. Like you don't have to do this update if lambda is 0. You can just do the one-step method. But they don't have it in the book, but I also have, here's the testing these methods on the corridor problem again. Remember, for the corridor problem, we only so far did the Monte Carlo methods. And there's a reason for that, at least if you look at the one-step method. So here is a parameter study on the corridor problem across a lot of different learning rates and a lot of different learning rates for the value function. And you can see that I said it's about negative 87 is the expected reward for the bad initialization that we took. And you can see here that basically there's no learning going on across all of these things. And the reason why there's no learning going on is because if you look at the one-step method, so here, this is undiscounted. So gamma is 1. Now, you know that our state representation in this problem is the same for all states. So v hat is the same everywhere. So if we look at this update, and we get a reward of -1. So delta, right, is just -1 on every single step. There's only one time delta is not -1, and that's when on the single step in an episode when it terminates, right? And in that case, we get -1 minus whatever our value approximation is, which is going to be really bad, right? It's going to be initially like -80 or something. I mean, we can actually see here what it ends up being. Right, so our value, so it's -96, and then this is just not, this is about like the policy we get when we start out with a bad initialization. So, right, in this method, because it's one step, we're doing bootstrapping. But because our state representation is the same everywhere, the bootstrap value is completely worthless. Like, it doesn't give us any information. Whereas in the Monte Carlo method, even though we didn't know what the states were, as we were going through, like we still had distinct values of G for every step in the episode, and based on what action we took. And what I said about like the gradient being biased or like introducing bias, that we're really depending on the value function approximation to give us some valuable information. And here, sort of by definition, it's not going to give us anything valuable because of how we've constructed it. So you can confirm here that there's just no learning going on. If you were to look at what the delta values are doing this update. So this problem really does not benefit at all from bootstrapping. And if instead you do it with the eligibility trace, actually, if we go back to the parameter study here, but we did it for 100 episodes. So the best value we got was like -15, right? Now we had said before, often problems. So like we know that the one-step return is worthless here. Maybe some intermediate value of lambda would actually help. Now, when we do Actor-Critic with eligibility traces, we introduce a lot of parameters. So you can do a parameter study here. So here, the most important learning rate is the policy function learning rate. That's the x-axis. I'll make different curves for the value function learning rate. And then on top of that, we have the two different values of lambda, which you could end up putting it in some complicated multi-dimensional plot. Here I'm just showing it where I can make a new plot if I change the values of lambda. Now, the lambda value for the state value function, it ends up being like fairly irrelevant. Like if I change this around, so here I get like -17 is the best result here. You can see as I'm like -18. If I move this over a huge range, it, it appears to be better. So as we get really to this extreme case, probably for some reason, actually, this is a case probably where you have to now substantially lower the state value learning rate. Yeah, so there's a way to get back to this sort of ideal value of around -19, -20. But you saw like varying this really doesn't move the needle that much. This, right, if I make this 1, so if I make both of these close to 1, this is now approaching the just reinforce with baseline method, right? Because I'm basically using close to a Monte Carlo return for both of these. But the result is still worse. I mean, I can try to make this, yeah, I mean, you can see the result is very similar to when I set this around like 0.92. We're getting around, between 17 and 20, the best result. This is over the same number of episodes, 100 episodes. So yes, in theory, you have the advantage that you can vary lambda and you can smoothly vary between these different methods. But the eligibility trace, the way this works, it doesn't, it's doing the step update in the middle of the episode, which usually is a benefit. But in this case, it doesn't perfectly mimic what we get with the Monte Carlo return. Even if we set lambda to 1, because we're not keeping the value function fixed like during an episode, like we are doing with the Monte Carlo method, usually it's not a problem. Here we can see we are getting some like learning result. It is working, but it's not working any better. It's actually a little worse than the Monte Carlo method. So all this added complexity of the eligibility trace and the actor-critic, I mean, if we're going to use actor-critic, we better use eligibility trace because like the one-step method completely fails. And here we only get decent results if we make the values of lambda so high that they're effectively the same as the Monte Carlo method, in which case we are better off just resorting to the, reinforce with baseline. There is, so far, these are all episodic problems that we have dealt with. There is a treatment of this, and I think actually the proof of the policy gradient theorem is a little bit more straightforward in the continuing case. Remember, for continuing problems, this is a case where we wanted to create a performance metric that didn't depend on the discount rate, which maybe sometimes seems kind of arbitrary if we pick a discount rate. And in the continuing case, we had already defined it for the like the policy improvement methods that used value functions, where we were instead trying to maximize the average reward per step, assuming that we don't actually finish an episode. We're just trying to, we have some environment where our goal is to get high rewards, certain actions, certain steps give us better rewards, and the goal is to maximize the average of that. Of course, the average only has meaning if we know the states we visit on average, which is why this definition only has meaning for a problem where we can define this state value distribution. And then from that, we can calculate, we want to basically have some policy that maximizes the number of time we spend in states that have high reward transitions out of them. And remember, when we had derived the policy gradient theorem for the episodic problem, we were using this other performance metric, right, which is just the this where we're taking the state value as the discounted value from some starting state, whatever the state is that we're starting an episode in. And that's how we had derived the update rule for the policy gradient. So we can derive the same sort of gradient update and show that it works for the continuing problem. And then we can also define like an actor-critic method that makes use of that. Now I could go through the continuing case now in the policy gradient and show the actor-critic for the continuing case, or we could just save it for next time when we do the continuing case and then maybe talk about this continuous action thing, and then probably just look at some other interesting examples that make use of policy gradient. So I don't know, it depends on how we want to structure the next meeting. And, you know, if people are already burnt out with what we've done so far. But what I discussed so far basically concludes the policy gradient methods for episodic problems. And then the remainder of the chapter is just, it has this section on continuing problems, and then sort of something without any examples, but just, you know, you could make use of this for continuous actions, and then a summary and conclusion. So we wouldn't finish the chapter now anyway, but it's just a question of whether it's worth going through the section on continuing problems or just saving it for later. But if no one has any preference, I'd probably just save it for next time, and then we can probably do that and then conclude the rest of the chapter at the next meeting.